Hello, everyone. So tomorrow, May the 1st, finally, it's going to be AP Chemistry exam. I just want to make sure that everyone can hear me. Okay, perfect. So today I will try to finish the unit 9, the application of thermodynamics, especially the electrochemistry part, because we're running out of time. I don't think I will go over the questions for unit 9, but instead I will try to go over a full AP chemistry test, both for MCQ and FRQ for 2018. Hopefully we'll have time to cover all of it within like 2.5 hours. So yesterday we talked about the thermodynamics. We talked about the enthalpy change for a reaction, enthalpy change of the formation, the bond enthalpy, the enthalpy change of the combustion. The best way to use the formula on the formula sheet. Oh, okay. SoCal stands for sulfuric acid, all of the three halogen acids, hydrochloric acid, hydrobromic acid, and hydroiodic acid, and nitric acid, the chloric acid. Do the 2019 one. 2019. Well, that works. I can do the 2019 if you guys want to do 2019. I have 2016, 17, 19, 18, 15, 14, 13, like 12. I have like all the packets from 2012 to 2019. Okay, so we're gonna 2019 later. So anyway, so let's get back to thermodynamics. So we haven't done any of the FRQ questions regarding thermodynamics yesterday. So I want to go over at least like one or two of them, and then we will get into the electrochemistry. So let's say for this one, under some conditions, SO3, sulfur trioxide gas decomposes to produce sulfur dioxide gas and oxygen gas. Okay, give me 1 second. I'm gonna explain KSP, the QSP. Okay. Under what temperature condition will the reaction be thermodynamically favorable? So thermodynamically favorable is the same terms as spontaneous, which means reaction just occur naturally without energy input. And delta G is less than 0 for thermodynamic favorability. Delta G is less than 0. High temperature, low temperature, or all temperature, or at no temperature. Justify your answer in terms of change. Okay, so delta H is obviously a positive value. And then delta G is change in Gibbs free energy is equal to delta H minus the temperature, which is measured in Kelvin, multiplied by delta S, change in the enthalpy. Well, so for change in the enthalpy, a lot of times we pay attention to the number of the moles. And we know that solid compared to liquid has a lower entropy, and then liquid compared to gas has a lower entropy. So the other way around, when you have more gas, then the entropy is getting higher. So I have only 2 moles of gas in the reactant side, while I have 3 moles of gas on the product side, which means when you go from the reactant to the product, the forward reaction actually increase the entropy. So for the forward reaction, entropy change is also a positive value. Okay, so both are positive. Okay, and then temperature, because it's measured in Kelvin, so it's also a positive value. Then at what temperature I will get a negative value of the delta G. Okay, that's when T times delta S is greater than delta H, which means the temperature has to be great enough to make sure that this is a greater positive value compared to delta H. So it is at high temperature. At high temperature, delta G is negative. Oh yes, all of you got the right answer. Delta S is positive, it's high temperature. And justify your answer in terms of the change in enthalpy and in the change in the entropy. Okay, and delta H, the change in enthalpy, is positive and delta S, change in the entropy, is also positive. So T has to be a large positive value to make sure that delta G, the difference, is negative. That's it. And then which year is this FRQ from? It's from either I don't know, either from 2018 or 19 or 2021 or 2022. And then someone just asked me about the KSP. Okay, so I will briefly talk about it, and then don't worry, I will go over everything later. So KSP, solubility product constant. So S stands for solubility, P stands for product, so it's solubility product constant. And then it means when you're going to dissolve a compound, dissolve a solid compound in water or in aqueous solution, then it dissociates into the cations and anions. So for example, silver chloride, AgCl in solid. Okay, when you dissolve in water, then it dissociates into silver cation, silver in aqueous, and then chloride in aqueous, and that it forms some kind of equilibrium, which means even though from the macroscopic perspective, I don't see any change in the amount of the silver chloride solid or precipitate in the solution, but the reaction is still going on. The forward reaction rate is equal to the reverse reaction rate. That's why you don't observe any of the change in the mass of the silver chloride in water, and then the concentration of these two ions. But they're actually constantly going back and forth. So it forms an equilibrium. And then for any of the equilibrium, we can always write the equilibrium constant as concentration of the products divided by the concentration of the reactants. And then raise the concentration to the power of the coefficient of that species. And now for this one, it's going to be concentration of silver cation, and then it has a coefficient of 1. So silver cation concentration to the power of 1 multiplied by the concentration of the chloride to the power of 1. And then you're going to divide it by the concentration of the reactant. But the only reactant for this chemical equation is silver chloride solid. And for solid and liquid, we don't have concentration, because concentration means the particles or the molecules are dispersed in a certain volume, and then the volume is changeable. And that's why when the volume gets big, it's diluted. So the concentration, this concept only applies to aqueous states or the gaseous states. For liquid and solid, they have the fixed volume. So the particles do not disperse to take the whole space of the container. So we're not going to take account the silver chloride solid. So we have for this equilibrium constant formula, we have only the concentration of the products. And let's say when Q is less than K, it's really soluble. And when Q is greater than K, it forms precipitate. Okay, so when Q is less than K, it means I have not enough products, which means to reach the equilibrium, the system should shift toward the right, which means now this solution can dissolve more of the compounds than how much it does right now. When Q is greater than K, it means there's way too much, way too many ions right now compared to the equilibrium. So the system will shift backward, shift in the reverse reaction, in the reverse direction, and then precipitate forms. When do we use S instead of X? What do you mean by S and X? Oh, the variable. Yeah, it doesn't really matter. You can use S, X, Y, Z, whatever the variable you want. If given a galvanic cell, how do you know which side of the anode and cathode is? So for the galvanic cell, galvanic cell means it's, okay, either for galvanic cell or electrolytic cell, it's the combination of reduction and oxidation. So redox reaction, they're occurring at the same time. But for galvanic cell, the cell potential is positive, which means it's a spontaneous reaction. And then the anode, okay, so an, ox, red, ket. So anode is always the oxidation, and then the reduction always occurs at cathode. So you're going to compare the cell potential, you're going to compare the reduction potential for each of the species, and then when you combine them, the E cell, the cell potential has to be a positive value for the galvanic cell because it's spontaneous reaction. Then now you know which one is reduction, which one is oxidation, and then based on that, you are going to like match the reduction side with cathode and then match the oxidation side with anode. So you are going to determine which side is oxidation or reduction first, and then you can determine which side is anode or cathode. Oh, cat fat. Okay. Do we have to know that what alloys are for the AP Chem test? I saw it in some of the practice, but no, you're not going to be tested on the types of alloys. So the most common types of alloy that you get tested is let's say zinc and tin, and then probably copper and zinc. And then it's going to be the still iron. So iron and then the carbon. But what's really matter here is not about you don't have to memorize anything, but usually for the alloy, it's going to give you the size of the atom, the size of the different elements in the alloy, and then it's going to ask you to choose which diagram represents a correct particle model of the alloy. Is it interstitial or substitutional? The bond angles, like bent, linear, tetrahedral. So for electrolytic cell problem, if the 2019 test have the electrolytic cell problem, I will go over it. And then write the K is less. Okay, so it sounds like a lot of people want to know about like comparison between K and Q. Okay, so it doesn't really matter if it's K or Q. Whenever you write the equilibrium constant, it's always the concentration of the products divided by the concentration of the reactants. Okay, the only difference between K and Q is for the K, you always use the concentration of the products and reactants at equilibrium. So at every single temperature, there is only one possible K value. But for the Q, you can just plug in any concentration. So the initial concentration of the reactants and products, or concentration of the reactants and product for now. So for Q, just represent where the equilibrium position is for now. And then when you're comparing Q to K, when Q is less than K, it means compared to the equilibrium, I have too little of the products. Because products are always on the numerator, and then the reactants are on the denominator. It means too many reactants, too little products. So to reach the equilibrium, the system needs to shift toward the right or shift toward the products. And if Q is greater than K, it means compared to equilibrium, I have too many products. Okay, too many products, too little reactants. To reach the equilibrium or to regain the equilibrium, the system should shift toward the left or shift toward the reactant side. At this review, I guess 2.5 hours. Yes, K is equilibrium, and then Q is the reaction quotient at some point in the reaction. Exactly. So sometimes Q might be equal to K. Then it means that, it just reached equilibrium. Okay, so going back to the enthalpy and then the Gibbs free energy question. This is the second question. 2H2O2, so hydrogen peroxide in aqueous decomposes into 2 moles of the water in liquid and then 1 moles of the oxygen gas. Hydrogen peroxide, Le-Chatelier's principle have to do with shifting? Yes. So Le-Chatelier's principle tells us in which side the system should shift to regain the equilibrium. Wait, alpha cell and beta cell? Do you mean for the cell? I don't think you need to know any of that. Okay, so let's go back to this question. I will try to answer your questions later. Hydrogen peroxide decomposes according to the equation. This reaction is thermodynamically favorable. So again, delta G is less than 0 at room temperature, which is a pretty low temperature. Shown below is a potential energy diagram for the uncatalyzed decomposition. 1, according to the diagram, is the decomposition reaction exothermic or endothermic. Okay, so this is the reactant, this is the product, and product has a lower potential energy, which means delta H is equal to, H product, the enthalpy of the product minus enthalpy of the reactants. And then because the enthalpy of the product is a smaller value, so delta H is a negative value. So obviously this is exothermic reaction. And then as for the justification, it's very simple. Just state that the products have lower potential energy than the reactants. That's it. So for a lot of justification or explanation question, you just need to state one sentence most of the times. And 2, manganese dioxide is an insoluble substance that acts as a catalyst for the decomposition reaction. On the diagram above, draw a curve that represents the reaction as it occurs in the presence of the catalyst. Okay, so what catalyst does is it speeds up the reaction, right? It speeds up the reaction and increases the reaction rate by providing an alternate pathway. Basically, it means it brings the multiple reactants all together, and then by then, it lowers the activation energy. So the difference between the reactant potential energy and then the peak is the activation energy. So this amount is lowered. So now I'm going to draw a lower peak. But as for the reactant and product, they still have the same potential energy. But is there a way to come to the conclusion without doing an ICE box? Most of the decomposition reaction are endothermic, yes, because decomposition means you are going to break the ionic bonds in the ionic compounds. I mean, if it's molecule, then obviously the bonds do not break. So for the decomposition or especially the dissolution, then it's going to break the bonds. When will the graph have more than one peak? Good question. So when there are multiple elementary steps, so let's say there are like 2 elementary steps, then most likely you are going to see like 1, 2, 2 peaks. If it's 3 elementary steps, you are going to see 1, 2, 3. Yes, I will try to go over the equilibrium part and acid parts later. Exactly, you need energy to break the bonds, then it's endothermic. Okay, so this part represents that you need energy to break the bonds, but then new bonds are formed. And then when new bonds are formed, the system also releases their energy, and then the amount of energy released is greater. So that's why in total, it's exothermic reaction. Okay, so let's see for this one. A student investigates the reaction between the silver in solid and then the nitric acid in aqueous. Predict the sign of the entropy change for the reaction. So again, I'm going to pay attention to the number of the moles of the gas. So for the reactant, I have 3 moles of the solid and 4 moles of the aqueous. And for the products, I have 3 moles of aqueous and then 2 moles of the liquid and 1 moles of gas. Okay, so gas has a really, really big entropy compared to liquid or solid, because gas, in the gaseous state, like particles are just far away from each other, and then they're free to move around in the container. So obviously the entropy has changed for the forward reaction. So delta S has a positive sign, and it's because the gas is formed for this reaction. How come when a reaction decreases the temperature, it is endothermic? Okay, so endothermic means the reaction or the species are absorbing the energy, right? Its potential energy is increased, but where does it absorb the energy from? It's going to absorb the energy from other elements or other species, like surroundings. So let's say in my bank account, like my deposit is going up. This is my deposit, and now my deposit goes up. Where do I get the money? I get the money from other people. Then for other people, their money is decreasing. They're losing money. So the surroundings are losing their energy while the system is absorbing their energy. So for the system, they absorb energy, it's endothermic. For the surroundings, they're losing energy, so their temperature goes down. And then for the exothermic reaction, it's the other way around. So let's say in my bank account, my money, I do see it and the number is going down. Okay, so where does money go? My money goes to like other people, like my friends, my family. So their money is increasing, right? So it's the same. When the system is releasing their energy, then their potential energy is decreasing, and then their surroundings are absorbing the same amount of energy. So their temperature goes up. So going back to this one, B, use the information in the table below to calculate the value of delta H, a standard enthalpy change for the reaction in kilojoules per mole. So now you're given the standard heat of formation for each of the species. And remember, when you're using standard heat of formation, you need to pay attention to the stoichiometry, the number of the moles. And then it's always the enthalpy change of formation of the product minus the reactants. It's the sum of the enthalpy change of formation of products minus the reactants. Okay, then I will just try to list the formula. Delta H for the reaction is, okay, then it's 3 times delta H formation of the silver nitrate plus 1 times the delta H formation of the nitrogen monoxide plus 2 times delta H formation of H2O liquid minus 4 times delta H formation of the nitric acid. Okay, so I don't have to, oh, oops, my bad. Okay, so for the reactant side, I don't have to add the enthalpy change of the formation of silver because enthalpy change of formation means you are forming this new substance is formed from its elements, and its elements in the most abundant form in nature. And silver, copper, zinc, gold, all of those metals, they exist in the form of the one single metal, the metal atom. So for all of these metals, and when they're in solid, the enthalpy change of formation is 0. For bonds, it's sigma R minus sigma P. Oh, yes, it's the reaction side, reactants minus the product when it comes to bond enthalpy. Okay, so Reva, I just answered your question, like why we don't have to worry about silver. So like all the metals are not the only species that we don't have to worry about the enthalpy change of formation. I said like oxygen gas, nitrogen gas, let's say, or hydrogen gas, or all of the noble gases such as neon or like xenon, helium, all of them. So they are the pure elements, and then they are in the most abundant form in nature. So if you ever have an oxygen on the reactant side or the product side, you don't have to consider its enthalpy change of formation. That's going to be 0. Or if it's helium, again, you don't have to consider its enthalpy change of formation. No, it's not because that's solid. It's because it's metal. So let's say sodium chloride, that's a solid, but it is a compound, and then its enthalpy change of formation is obviously not 0. It's because we're gonna write this when we write the standard heat when we calculate the standard heat of formation, we write the formation reaction chemical equation, and then for the silver, it's from the pure element silver to the silver. So there's no change. It's already in the pure elements form. And then, well, I'm not gonna go through the calculation part. You can just use the calculator. So for now, let's try to go over all the concepts. And now it's D. Wait, what is the question? Use information. Oh, what I just did is question number B, not C. Okay. And then based on your answer to parts A and B, is the reaction more likely to be thermodynamically favorable at 25 or at 95? Well, to answer that question, actually, I will have to calculate the answer for B. Okay, so the answer for B, that's going to be 3 times negative 101 plus 90 plus 2 times negative 286 minus 4 times negative 207, which is 43. Okay, it's positive 43 kilojoules per mole. So it is a positive value, and delta S change in entropy is also it's also the positive value. Okay, so for delta G, Gibbs free energy change is equal to delta H minus temperature times delta S. And now I know both of them are positive value. Okay, so to make sure that delta G is a negative value for thermodynamically favorable, delta G is negative. Then the temperature has to be a larger positive value. So it's more likely to be thermodynamically favorable at 95 Celsius degree. because this is a higher temperature. So justify your answer. Okay, because both delta H and delta S are positive, so delta G is more likely to be negative at higher temperature. That's it. Do we have to get all the units right in parts A, B, and C to get the units point? What do you mean? Get all the units right? What do you mean by do we have to get all the units right? Oh no, so do you mean the grading? No. So for usually most of the questions is like 1 point, one or two. You barely see like 3 points for each of the small question. That's 1 point. So let's say like usually like these are 1 1 and then like 1 1. For some of them, if the justification is pretty long, then it might be 2 points. For some of the question, it's asking you to justify by like two different points or like specify like two different stuff, then it might be 2 points. Usually it's 1 or 2 points. When you say if you miss 1 unit, when you say like, oh, the unit. Okay, so I'm not an AP reader, so I can't really tell. But for me, I prefer to put all the units just to make sure that I don't get any points off. But for some question, I think if the reader isn't that strict, then it should be fine without the unit. How do we know how much do we have to explain? Okay, so for most of the AP FRQ questions, unless it has stated that you need to put like 2 points, or give me like 2 explanations or like 2 aspects, usually like one sentence is enough, like 1 to 2 sentences is enough. If you take a look at the if you take a look at the College Board, the FRQ, the scoring guideline, usually it's just like 1 sentence with like 1 or 2 keywords. Oh, if we say kilojoules per mole, and the answer says kilojoules per mole, no, you are gonna get the point. You will get the points. Like kilojoules per mole is completely correct. Like there's nothing wrong with like missing like reaction. Yeah. So to be honest, I feel like even if you put kilojoules, just kilojoules, if the number is right, I think you will get the points. Yeah, and those are very trivial, like kilojoules per mole and kilojoules per mole like reaction. That's basically the same. And D, the students run the reaction using a 3 to 4 mole ratio of silver solid to the nitric acid aqueous. Suggests a method the student can use to isolate solid silver nitrate from the other products of the reaction. Okay, so this is an aqueous, this is in gas, and this is the liquid. So obviously gas wouldn't mix well with the aqueous or the liquid. So what I have to do is you will have to separate the solid silver nitrate from the solution, because eventually for the product, you will have silver nitrate and then the water. Okay, so basically, okay, silver nitrate, it's pretty soluble in water. So how do you separate silver nitrates from other products? What is the easiest method to separate to separate the solid and the water? Just evaporation. That's it. If gas isn't forming, the product is evaporation. Great. Yeah, is delta S negative then? So if gas is not produced, to be honest, then it's going to be kind of it's kind of ambiguous to tell. So in AP chemistry, usually you wouldn't be tested on something so ambiguous. Because for the solid and the liquid, I mean, of course, the liquid is slightly more has like slightly like less slightly more disordered, but usually you're not asked to compare the entropy of the solid or liquid. Usually like it's gas involved. Then it's very obvious that the size with more gas has higher entropy. No, you don't need to explain it. Okay, so let's say suggest a method. It didn't say justify your answer. It didn't say explain it. It didn't say, oh, you need to put each of the step. Then evaporation, just one word, you will get the points. To get a 3? Wait, what is the cutoff line for 3? Probably half of it. Probably like 30 out of 60. If it says justify, how would you write your answer? Okay, good question. So if it says justify, first off, so there are 3 species for the product, and gas. Okay, so gas wouldn't be mixed with the aqueous or the liquid. So gas will be okay. So for the product, I will just have the liquid parts all together, and then above that I have gas. So they're naturally separated. I only need to worry about separation of these 2 species. Okay, so this is just pure water, and then silver nitrate, it's soluble, but it's ionic compounds. So the way to separate the solids dissolved in a water is to evaporate. That's it. So once you evaporate it, all the water is gone, and then because this is when you heat it up, it will just form a precipitate or form the crystals. So the leftover after the evaporation is the silver nitrate. Yeah, I think for 3 it's approximately 50%. But I mean, the cutoff line differs from year to year. So for some years when the test is easier, I do see that like you have to get like 77, 78. When it's a little bit more difficult, like 72, 73. But usually I suggest my students to get at least 75 out of 100 to make sure that it's a safe 5, or like 76, 77. Okay, so now let's try to okay, so before getting into 2019 question, I want to try to answer all the questions first. So if you have, I think somebody asked me to go through the bond angle. So now it's time to ask me any questions from unit 1 to unit 9, everything. I will start from the bond angle. So for the bond angle, then when you need to know the Vosper theory, of course, the valence shell electron pair repulsion. Okay, so what is used for is to determine the molecular geometry of any of the molecule. And then when we learn molecular geometry, you've learned another term which is very similar, which is called electron domain geometry. Okay, so the theory behind the Vosper is that it states that electron pair, okay, electrons repel each other because they are like charges. Unlike charges attract, like charges repel. And then when I say electron pair, it includes both the bonding pair and then the lone pair. So for example, for water, H2O, first off, we need to start from the Lewis dot diagram. Okay, so oxygen in the middle, and then oxygen is a central atom. It's bonded to 2 hydrogen by single bond, and then the oxygen has 2 lone pairs. So how many electron pairs does the central atom oxygen have? Now it has 1, 2, 3, 4. So including the lone pair, it has 4 electron pairs in total. These 4 electron pairs repel each other, and they want to be furthest away from each other. They want to be far from each other as much as possible. And then when you have 4 electron pairs surrounding the central atom, the most ideal structure is the tetrahedral. So the central atom, and then you have 1, 2, 3, 4. So it's like a tripod and then with a head on top of it. So like imagine you have a tripod and you're gonna put your iPhone, so you have a stick on top of it. So that's like four legs in total, like 3 legs and then 1 stick upward. And then but 2 of them are actually the lone pair electrons. Okay, so 2 of them are the lone pair electrons. And then, so for the electron domain geometry, we take into account both the lone pair and then the bonding pair. So electron domain geometry for water is tetrahedral. But when it comes to molecular geometry, I only care about the atoms. I only care about the bonding pairs. So only these parts are the molecular geometry. Only these parts are the molecular geometry, which is bent. So this is why the water has the bent shape. And then for the bond angle, okay, so for a regular tetrahedral structure, the bond angle is 109.5 degree. The thing is, when you have the lone pair electron, so lone pair electron exert a little bit greater force than the bonding pair. They repel each other a little bit stronger. So which means when you have two of the lone pairs, they're gonna push the bond pairs closer to each other, but only slightly, only by very small fraction. So these angle, the bond angle, will be slightly less than 109.5. So for water, it's approximately 105 degree. But it doesn't matter. It's not going to ask you to put like 105. Even if you put 109.5, usually it's correct. It's considered correct. You are not required to memorize this for AP exam. Or if you put slightly less than 109.5, that's also correct. The galvanic cell. Yeah, I will go over that part. Okay, so the most typical type of the molecular structures, like molecular geometry, you will be tested is the tetrahedral and then trigonal planar. So trigonal planar is something like let's say BH3, the boron trihydride. So boron has 3 valence electrons. So when it's bonded to 3 hydrogen, this is the structure. So how many electron pairs? So it has 1, 2, 3 bonding pairs, and boron does not have any other lone pair electrons. So it's 3 electron pairs, and then when they repel each other, so they are furthest away from each other, the bond angle is 120 degree. So they're on the plane, they're on the same plane, and then they're 120, 120, 120 away from each other. This is trigonal planar. And then let's say ammonia, NH3. Okay, that's also a typical type of molecule you get tested in AP chemistry. Okay, seesaw. I will go over the seesaw. So NH3. Okay, so ammonia, and then you have 3 hydrogens surrounding it. 1, 2, 3, and then ammonia has the lone pair electron. So you have 1, 2, 3 bonding pair, and then the 1 lone pair. So NH3 has tetrahedral as electron domain geometry. But again, when we consider the molecular geometry, I don't care about the electron, the lone pair. I only care about the atoms or the bond pairs. So for the molecular geometry, it has this trigonal pyramidal structure. So it's basically a tripod. Okay, and then let's do the seesaw. Yes, you'll be tested on you wouldn't be tested on electron domain geometry, but you will be tested on molecular geometry. But to figure out the molecular geometry, you have to know the concept of electron domain geometry. Are they gonna ask us to exact molecular? Yeah, they might ask you like what is the molecular geometry of the structure in FR2 question. Not very often, but they might ask you. Or most likely, you're not gonna be directly tested on this, but you are gonna be asked, oh, is this a polar molecule or non-polar molecule? Or you will be asked to compare the intermolecular force. That intermolecular force depends on if this molecule is polar or non-polar. And how do we determine if a molecule is polar or non-polar? It depends on molecular geometry. So for example, for tetrahedral structures such as CH4, okay, so it's 1, 2, 3, okay, tripod, and then tripod, so 3 legs, and then 1 stake upward. So CH4 is perfectly symmetric. So it has this tetrahedral structure, which is already symmetric, 3-dimensionally symmetric, and then each of the bonds are equal. So this is perfectly symmetric. And symmetric means that this is a nonpolar molecule. Then what about ammonia? Okay, so ammonia NH3 is not, this is polar because the structure is non-symmetric. Okay, why is it not symmetric? Okay, so to be honest, the tripod part, 3 of the fit, they are actually symmetric, but at the top we have this electron pair. So like up and down, like vertically, they are not symmetric. So this is a polar molecule because of the asymmetric structure. How is the pyramidal and not trigonal planar? Both of them have 3 bonds. Oh, do you mean like, okay. Again, we need to determine like number of the electron pair, and the number of the electron pair includes the bond pair and then the lone pair. So nitrogen is surrounded by 4 lone pair, 1, 2, 3, 4. So with 4 electron pairs, its electron domain geometry is tetrahedral. But when you name it, when you name the molecular geometry, you don't care about the electron pair. So you are going to only take a look at these part of the structure, and then we call it trigonal pyramidal. On the other hand, for boron trihydride, boron has only 3 electron pair. So at the very beginning, so from the very beginning, these 3 bonds, they are 120 degrees away from each other on one single plane. So that's trigonal planar. If it asks us to see if it's polar or nonpolar, we could use the geometry as a justification, yes. But for polar and nonpolar, usually it's not going to ask you to justify that. Usually it's in the MCQ question. Yes, so first step, write the Lewis structure. The second step, find out the number of the electron pairs. 3, find out the electron domain geometry. 4, find out the molecular geometry. Yes, if it's symmetric, it's nonpolar. How is CH4 symmetric? Okay, so 4 bonds. So it's a 3-dimensional thing. So I don't have that. I don't have the model right now. Okay, so this is a 3-dimensional. This is a three-dimensional sketch. Okay, so again, imagine that this is a tripod. So you have like 1 atom here, and then 1, 2, 3. You have 3 of the fit. Okay, so 3 of the fit. And then on top, you have like 1 more bond sticking upward. And then when you flip it by 109.5 degree, okay, let's label this as hydrogen 1, hydrogen 2, hydrogen 3, and hydrogen 4. Let's say you're going to flip it by 109.5 degree. Then it's going to be exactly the same look. So when you flip it, so hydrogen 2 is pointing upward. Then hydrogen 1 is pointing downward. And then now this is hydrogen 4, and then now this is hydrogen 3. It's exactly the same tripod structure with the stick pointing upward. And then which of the following molecule contains the polar covalent bonds? Okay, so I'm going to go over that question. So first up, let me finish the seesaw structure because I think someone asked me about the seesaw. So seesaw structure occurs when the central atom has 5 electron pairs. Again, electron pairs include both the bonding pair and then the lone pair. So such as PF5, phosphorus pentafluoride. Okay, so the phosphorus is covalently bonded to 5 of the halogens, fluorine. Okay, so how they form the balance in 3D world is, okay, P is the central atom, and then up and down it has 2 of the fluorine. Okay, and then now we have a surface that is perpendicular to this surface is perpendicular to these bonds. So this is vertical, this is horizontal plane, okay? On this horizontal plane, the phosphorus has 3 more bonds. 1, 2, 3. So they are 90 degree. The bond angle here is 90 degree because all of these 3 are on this plane, on this horizontal plane, while this bond is vertical. So the bond angle here is 90 degree. The bond angle here is also 90 degree. Bond angle here is also 90 degree. And for the bottom fluorine, that's the same. The bond angle is 90 degree. This is also 90 degree. This is also 90 degree. And then on this plane, these 3 bonds are like far away from each other by 120 degree. Okay, and then this is a base structure. And then what happens here is when you replace one of the fluorine with the lone pair, then it forms the seesaw structure. Well, what are some examples? So let's say, I think it's SF4. Yes. So that's going to be sulfur, and then 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2. Yes. So okay. So sulfur, it's gonna have fluorine up, fluorine down, and then on this horizontal plane, it's going to have one fluorine bond, another fluorine bond, and then on the other side, it's gonna have the lone pair electrons. Okay, so again, the electron domain geometry of SF4 is, this is trigonal bipyramidal because you have a triangle on the plane and then it's pointing upward. So this is a trigonal pyramidal. And then you have another trigonal pyramidal that's pointing downward. So you have 2 pyramidal. So it's called trigonal bipyramidal. That's the electron domain geometry. But when it comes to molecular geometry, I'm not going to take into account the lone pair. So it's going to be a seesaw structure. So this is vertical. These 2 are on the plane, on this horizontal plane. So they are like this. This is a seesaw structure. And of course, this is polar. This is non-polar. Memorize all the bond angles and the shape. Yeah, you have to memorize all of them. So would it be less than 90 degrees? The seesaw is 120 and 90. Yes, it will be 120 and 90. So for the seesaw, again, as I said, the electron pair, or sorry, the lone pair is a little bit stronger when it comes to pushing or like repelling the other bond pairs. So the electron pair will actually push these 2 bond pairs slightly closer to each other than the regular structure. Than the regular trigonal bipyramidal structure. So this angle will be slightly less than 120. But as I stated before, in AP Chemistry, you're not required to memorize that exact number. So if you put like slightly less than 120, or if you just put 120, both are considered correct. Oh, so this is seesaw. Okay. And then this one is trigonal bipyramidal. Wait, bipyramidal. What about the octet rule? Okay, octet rule. Okay, wait. There are too many questions. Why does the seesaw structure have a 120 angle and a 90 degree angle? Okay, so again, how do we get the seesaw structure? So seesaw structure for seesaw, seesaw is the molecular geometry, and its electron domain geometry is 1, 2, 3, 4, 5. Its electron domain geometry is the trigonal bipyramidal. For trigonal bipyramidal, we have 90 degree because these 2 atoms are 1, 2, 3. These are linear. And then that's a vertical. And then perpendicular to the vertical line, we have a horizontal plane. On this horizontal plane, we have 1, 2, 3, 3 bonds. So these are 180 away from each other. And then anything on this plane is 90 degree away from this fluorine and 90 degree away from the other fluorine. And on this, within the plane, these 3 are 120 away from each other. So is T-shaped 90 degree? Okay, so for the T-shape, exactly. So for T-shape means based on this electron domain geometry, you are going to replace 2 of the bonding pair with electron pair, with lone pair. So now we are left with 1, 2, 3 bonded atoms. So it's T-shaped, so that's 90 degree. So everything in row 3, aluminum, silicon, and below can have extra electrons on central atoms. Wait, is somebody asking me about the overfilled octet and underfilled octet, like extra electrons on a central atom? Okay, so on the periodic table, everything that's that's in group 4, no, not group 4, group 5, 6, 7, 8. So anything 1, 2, 3, 4 here. And so anything on the right side of the carbon and silicon. So group 5, group 6, group 7, group 8, if they're the central atoms and if they're bonded to like halogen, then they can have like overfilled octet. So for example, xenon fluoride. I think it's xenon tetrafluoride. So xenon is a noble gas, and usually it does not form covalent bond, or it does not form any of the bonds with other atoms, but there are some exceptions. So if it's xenon, it has fluorine, 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 and then it has 1, 2, 3, 4. Yes. So now eventually xenon tetrafluoride has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It has 12 valence electrons, which is greater than 8. So it's not following the octet rule, but this is already the best or the most ideal, the molecule, the Lewis structure that I can come up with. So for xenon, some atoms like xenon, then if it's the central atom and it's bonded to the halogen, then it's overfilled. Then it reached this overfilled octet state. And for xenon tetrafluoride, it has 1, 2, 3, 4, 5, 6 electron pairs. So for 6 electron pairs, it's going to be this wait, what is it called again? Octet? It's 1, 2, 3, 4, 5, 6. Oh, it's like octahedral. Yes. So it's like fluorine, fluorine, fluorine. Actually, no. These two fluorine are on one single plane. Fluorine, 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 fluorine. And then on the up and down, it has the lone pair electrons. So it's like X, Y, Z axis. X, Y, Z axis. So each of the axes is 90 degrees from each other. So the bond angle is, of course, 90 degrees. And then it has the square planar shape. And then, of course, it's symmetric, so it's nonpolar. Can H2O cause hydrogen bond? Yes, of course. Like water molecule is one of the typical one that has the hydrogen bonding. So that's why water has relatively high melting point and boiling point. What about the other 3? Okay, H2O, H2S, H2S, H2SC. Okay, so oxygen, sulfur, selenium, and tellurium. Okay, so H2O, it has the hydrogen, the greatest, the boiling point because of the hydrogen bond, and then the other 3 does not have. The other 3 don't have the what is it called? The hydrogen bonding, right? But then they also have their molecular geometry is polar. Their molecular geometry is not symmetric, so they're polar. And then, okay, so except for the oxygen, when these 3 combine with hydrogen, okay, so when you go downward, the atom size is getting bigger. When atom size is getting bigger, it means their electrons are getting, there are more electrons. So more electron means that more of the polarizability is getting bigger. So bigger polarizability means the greater London dispersion force. So H2O has the highest boiling point, and out of the other 3, it's going to be H2S less than H2 selenium less than H2 tellurium, because when you go down, a bigger atom, which means more electrons, and more electron means a greater or larger polarizability, and larger polarizability means a greater London dispersion force. The photoelectron spectroscopy? Okay. Oh. The resonance? Okay, how do you know when it's just molar? Okay, so first off, I will try to go over the galvanic cell and the electrolytic cell, and then the Gibbs free energy and then Faraday's constant. Okay, so galvanic cell versus electrolytic cell. So the difference between them is in the redox reaction occurs in both of them, but one of them is spontaneous and the other one is non-spontaneous, which means if I want the redox reaction to occur, then I need like extra energy. I need extra like battery source. So electrolytic cell is like non-spontaneous reaction. So we need extra battery source. And then for the galvanic cell, that's spontaneous. So it just occurs naturally. Two molecular compounds with one LDF, the only things that you can use to compare them is size. Yes. The wavelengths, Planck constant. Okay. Galvanic, like to the opposite. Yes, galvanic cell and the electrolytic cell, they're like opposite. Okay, so for the galvanic cell, you are going to have two separate containers. Okay, in each of the container, you will have the solutions. And then the cathode and the anode. And they're just connected by this wire. So let's say on one end, let's say you have the oxidation reaction. Then this is considered anode. And on the other side, you have the reduction going on. Then this is considered a cathode. Okay, so for the oxidation, it means it's losing electron. So let's represent this anode as X, element X. Then when it's losing electron, then it means it is converted to X plus or X2 plus. Anyway, it's converting to cations. Okay, so what it means is the part of the anode is decomposing into the cations and it's dissolving water. So you will observe that it's getting smaller and smaller. So these parts are like dissolved into water and then they form more of the cations. And it releases electrons. So electrons are moving to the left. Electrons moving to the left toward a reduction. So for the reduction, it's gaining electrons. So when it gains an electron, okay, let's represent it as Y. And then in the solution, we have like Y, let's say we have Y plus. Then it's going to capture the electron and then it's going to it's going to be deposited on the cathode. So cathode is getting bigger and bigger. Kinetic molecular theory and, okay. And on the other hand, okay, and then you also need a salt bridge. Okay, so salt bridge is just to balance out the concentration of the cations and the anions. So let's say on the cathode side, you will see a decrease you will observe a decrease in the cations. So you wanna compensate for that loss. So you want whatever the cations to move to the left, and then you want anion to move to the right. Solve what do you want me to solve? Okay, so for the electrolytic cell, on the other hand, you need a battery. And then usually for the electrolytic cell, like two of the cathodes and anodes, they're in the same container. Okay, I will try to solve as soon as I'm done with the galvanic cell and electrolytic cell, okay? And they are connected by this external battery source. So electrons are getting out, so it's moving toward this side. And of course, electrons are moving toward the cathode side. So the reduction is occurring because the cathode is gaining electron. And then electrons are deprived from the anode side. So it's oxidation going on. Have the salt bridge, the galvanic cell have the salt bridge? Yes. Okay, and then now let's talk about how the redox reaction is related to the Gibbs free energy. So Gibbs free energy delta G under the standard condition is equal to negative of the number of moles of the electron transfer multiplied by the Faraday's constant multiplied by the cell potential. Okay, so we know how to calculate the cell potential, right? So cell potential is equal to, according to whatever that's written on the formula sheet, that's the reduction minus the oxidation. But to be honest, this is not what I prefer, because I feel like this is very, very confusing to me. So what I prefer is I just prefer to write to reverse the oxidation and then just add up all the cell potential. So for example, let's say we have a redox reaction of copper in between like silver and copper, okay? So let's say silver reacts with like copper cation, and then they form two of the silver cations and then one of the copper atom. Okay, then first off, I will have to separate them into two of the half reactions. One is silver into silver cation to produce one electron, and then the other one is copper gaining two of the electrons to form copper. Okay, so for the cell potential, what's kind of important here is the stoichiometry doesn't matter, because cell potential is like that's like a difference in the height. So the difference in the height doesn't change when you try to, let's say water drops from a high altitude to a low altitude. So the stoichiometry, or the number of moles, represent the amount of the water flow, but the amount of water flow does not affect the difference in the height. So the cell potential, you don't have to multiply the cell potential by 2. So that's different from all the other like calculation. And let's say, and then, okay, so the reduction, I need to pull up this reduction potential table. So on this reduction potential table, so the reduction potential for copper is 0.34 voltage. And then the reduction potential for silver is reduction potential for silver is positive 0.8. Okay, but that's the reduction potential for silver. And now the silver is actually going through the oxidation. So I'm going to take the negative of the reduction potential, which is negative 0.8 voltage. And then now I'm just going to add up these two reduction potential value. So the cell potential for this reaction is negative 0.8 plus 0.34. So I prefer to do addition rather than reduction, because I just get confused if it's like reduction minus the oxidation. Okay, and then once you know the cell potential, now you can try to calculate the delta G, the Gibbs free energy. Again, this is under the standard condition. And what we mean by the standard condition is when the concentration, when the K value is equal to 1. When we assume that the concentration on both sides is equal to 1. And Ne refers to transfer of the electrons, the number of the electron transfer. So for this reaction, okay, so because we have copper 2 plus, and then I have 2 of the silver plus, so I know that for this reaction, the number of the electron transfer is equal to 2. So Ne is equal to 2. And then now we know that E cell, the cell potential is negative 0.8 voltage. And then F is the Faraday's constant. You just multiply them together, then you will get the delta G. And remember that delta G and cell potential always have the opposite signs. So for delta G of less than 0, this is considered thermodynamically favorable. And for thermodynamically favorable reaction, for redox reaction, the cell potential is always greater than 0. For thermodynamically unfavorable redox reaction, the cell potential is always less than 0. Do you flip the one with a lower reduction potential? Wait. If we change the sign down, yes. Okay, so let me rewrite it. So for the reduction potential, because you are given the reduction potential only on the formula sheet. Reduction potential for silver has the equation like this. And then the corresponding reduction potential is positive 0.8 voltage. And then for the reduction potential of copper, it's positive 0.34 voltage. So usually on the formula sheet it says, oh, reduction minus the oxidation, but that's not the way I prefer. So what I prefer is, okay, so to eventually get silver combining with copper cations to get silver cations and then the copper. So you will have to flip the first equation. So it has to be silver release electrons. And for this reduction, because you reversed it, so you are going to put a negative sign in front of the reduction potential. So now for this reaction, we have 0.8 voltage as the potential. And then I'm just simply adding up these two. Of course, I will have to multiply it by 2, but for the reduction potential, as I stated before, you don't have to multiply the cell potential by 2. You don't do that. You never do it. For cell potential, you don't consider stoichiometry. And then you simply add up these two, which means now you're going to add up 0.34 and negative 0.8. We always want a positive. I mean, for the galvanic cell, we always want a positive, but I mean, so I didn't really specify if this is for galvanic cell or for electrolytic cell. So if you don't multiply 2, does it matter if you do the stoichiometry? It does matter when it comes to number of the electrons, because number of the electrons do have to match, like 2 electrons on the reactant side, 2 electrons on the product side. So you have to multiply by 2, which means for every 2 moles of the silver, and it's going to produce 1 mole of the copper atom. So it does matter when you write the redox reaction, it does matter. But when you're calculating the cell potential, you don't multiply by 2. Yes, when you write the official reaction, you will have to include the 2. You will have to multiply by 2. This is a balanced equation. If you put only 1 silver, then to be honest, this is not balanced because the number of electrons do not match. You need to have the same number of electrons on the reactant side and then on the product side. How do you know which reaction to flip when you have the reduction potential? Let's say, okay, so let's say silver and ceranium, okay? So let's say, okay, given that it's galvanic cell, then it means it's spontaneous reaction. Spontaneous means thermodynamically favorable, delta G is less than 0, and then the cell potential, we know that it has to be greater than 0. Okay, now let's see. So first off, I will try to write down the reduction equation, the half equation for both. So for silver, this is the reduction for the silver cation, and that's positive 0.8 voltage. And then for the ceranium, what is the, okay, ceranium, I don't know what is a reduction potential for ceranium. What is the reduction potential? Oh, for ceranium, okay, so ceranium 2+, when it captures 2 electrons, then now it becomes ceranium atom, and its the reduction potential is negative 2.89 voltage. Okay, then, okay, so when you combine them, you will need to get a positive value. Okay, so either you are gonna flip this one, so it becomes positive 2.89 plus 0.8, or you are gonna flip this one, so it becomes negative 0.8, and then you add it up to negative 2.89. Wait. Why do we have to flip it if it's being oxidized? Okay, so both of them are reduction. And for the redox reaction, one of the half reaction is reduction and the other half reaction is oxidation. You are combining reduction and oxidation. So they form a redox, a pair of redox reaction. So you will have to flip one of them anyway. So either you flip this one and add them up, or you flip this one and add them up. So which one, in which situation do I get a positive cell potential? Obviously, when you flip this one and when you get a positive 2.89. and then add it up to negative 0.8. So I know that for galvanic cell, if it's galvanic cell and if it's spontaneous reaction, then it must be, the redox reaction must be silver cation and the serenium to produce silver atom and then the serenium cation. And then now I try to balance it out. And after I balance it, it's 2 in front of the silver ion and silver atom. Okay, so for this one again, okay, so for if you flip it, if you flip the serenium one, then you get this, and your cell potential now becomes negative of the, okay, now it becomes positive 2.89 plus 0.8, which is a positive value of 3.79 voltage. But if you flip the first one, now our reaction is silver atom reacts with serenium ion, and then it forms silver cation and then the serenium. And then for the second one, the cell potential becomes flipping the positive 0.8, so negative 0.8 plus negative of 2.89, which is negative 3.79 voltage. So for this redox reaction, it cannot occur in a galvanic cell. We know the E cell value and one of the reduction potential values, but we are trying to find another. Okay, trying to find another. Do I have to flip it? No, you don't have to flip it if you do the cathode minus anode or reduction minus oxidation. Like that's just a method that I don't prefer because I always get confused about like which one is reduction and which one is oxidation. So I prefer just addition rather than subtraction. Okay, so, well, I'm so sorry, guys, but we're running out of time. So I think we should start to do the 2019 questions. And then while we go over all the MCQ questions, I will try to explain every single concept. I wouldn't just go over it and then just choose the answer and then just go to the next one. So 2019. So for 2019, okay. Okay, and then feel free to ask me any questions if you have any. I will start with MCQ because we went over kind of like a lot of FRQ questions in the past couple of days. So I want to go over the MCQ questions first, and then we might not be able to go over all the FRQ questions, but I will try my best. Okay, so let's start with question number 1. And then if you guys want to know the answer, you can just type it in the chat box. Feel free to type your answer in the chat box. 1, in which of the following process will delta S be negative? Well, we literally just talked about the entropy change. And then I said the number of the gas molecules does really matter. D. Perfect, because it's going from gas to the liquid. Perfect. So it's the particles are getting closer to each other. They're getting more ordered. So the entropy is decreasing. So it's getting negative. Perfect. Question number 2. Of these 3 solutions listed in a table, okay, which one has the greatest electrical conductivity and why? Okay, so electrical conductivity depends on how mobile the cations and anions are, or how mobile the electrons are. So the more of the electrons you have in a solution, or the more of the ions you have in a solution, the greater electrical conductivity. Okay, so a lot of people give me the answer B. So B states that 0.1 molar of the potassium iodide. Perfect. It's because this is the only ionic solid, so it completely dissociates. So you will have 0.1 molar of the potassium cation and 0.1 molar of the iodine anion. On the other hand, for these two, they are both like weak acids, and weak acid only partially dissociates. So once they're dissociated, you will see only, let's say, like 10 to the power of negative like 4 molar of, let's say, the protons, or 10 to the power of negative 5 molar of the protons. You will see only very small number of the ions for the first one and then the third one. So the answer is B. Great, perfect. Yes, ionic compounds always completely dissociate. Ionic compounds. And then remember that such as potassium nitrate, this is also ionic compounds. So nitrate, NO3 minus, it's polyatomic ion. Still, it's an ion. So it dissociates into potassium and then the nitrate. So let's say if we're going to compare these two solutions, then their electric conductivity will be exactly the same, given that their concentration is the same. And next one, hydrogen gas reacts with oxygen iodine gas, and then it forms an equilibrium in between 2 moles of the hydroiodide gas. It reacts at constant temperature in a sealed rigid container, and the gas are allowed to reach equilibrium. Which of the following best describe what will happen to the reaction immediately after additional iodine gas is added to the system? Okay, so it's already at equilibrium, but the equilibrium was like damaged. It's broken because additional iodine. So it's Le Chatelier's principle. So Le Chatelier's principle states that when a system is in equilibrium, and then you break the equilibrium by adding a pressure or stress on one side of the equation, then it's going to shift toward the other side to compensate for the loss or compensate for the gain. Well, a lot of people write C and an A. Okay, so additional iodine gas. Okay, so concentration of the reactants has increased, which means I will have to like decrease the concentration of the reactant side. So it should shift toward the product side. See, the rate of the forward reaction becomes greater. Yes. So at equilibrium, the forward reaction rate is the same as the reverse reaction rate. But once it's shifting toward the right, the forward reaction rate is getting like bigger. So it's C. Perfect. Okay. All of you guys are doing great. And next, ionization energy. That's the periodic trend that you learn in Unit 1. The first 5 ionization energy of an unknown element. So this is another like typical type of questions that you'll be tested regarding ionization energy. It's going to list a bunch of the ionization energy, and then it's asking in which group it is, or which of the following element it might be. Okay, so 578 to 1,800, and okay, so this is a jump, and it's approximately like 3 times bigger. And then next, it's approximately like 0.8 times bigger. Okay, and next, this is like from 2,700 for 2,700 to 11,000. That's like about like 4 times bigger, right? Okay, so and then now this is only like sorry, this one should be about like let's say 1.5. This is approximately just 1.2. Okay, so which one is the biggest step, the biggest increase? So the biggest increase is from 3rd to the 4th, and that's because after you have removed 3 electrons, it has reached that full octet state, or the noble gas state. So for the noble gas, it requires a lot of energy to remove an electron because it's in the perfect or very stable octet state. So it means once you have removed 3 electrons, now this atom is at the full octet state, which means it has 3 valence electrons. Exactly. So that's going to be B, aluminum. Okay, all of you guys are doing great. And next, question number 5. The diagram above represents a particle in aqueous solution. Obviously, in aqueous solution, it means water. So these are water molecules. And obviously, the small one is H. The bigger one, the dark one, the gray one is oxygen. And then the hydrogen side is facing toward this particle, which means, okay, the hydrogen carries the partial positive charge, and then oxygen carries partial negative charge, which means this must carry a negative charge. So which of the following statements is correct? A, the particle must be cation. Okay, it must carry a negative charge, so not A. And then the answer should be B. Great. It should be the anion because the positive end of the water molecule is pointed toward it. Okay, what about C and D? The charge of the particle cannot be determined. Well, no, it can be determined. Okay, D, the charge of the particle cannot be determined because it's arranged symmetrically. No, it has nothing to do with it has nothing to do with the arrangement of water. So if it's like anion, then all the hydrogen are facing towards the ion. If it's cation, then the oxygen part will be facing toward the ion. Yes, given that we can finish MCQ questions within like 2.5 hours, I will try to go over FAQ. And next, there are two compounds, hexane and octane, and their formula and boiling point is given. Well, even without reading the question, I know this is about intermolecular force or the boiling point. The student obtains a mixture of liquids, blah, 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 which are miscible in all proportions. Miscible means they're soluble. And which of the following techniques would be best for separating the two components of the mixture? Oh, okay. So it's not asking about the intermolecular force. It's asking about the method for the separation. So both are liquid. Okay, so when you're trying to separate two liquids with different boiling points, the technique you use is the distillation. So it's used to separate two liquids with different boiling point. When do you use evaporation? Okay, when do you use evaporation, guys? What's the difference between distillation and evaporation? Like, I mean, for both of them, I need to heat up the sample I have. When you use the chromatography, okay, so for chromatography, it's like you don't even know the boiling point of different substance, and it's all, again, the liquids, and then it depends on their molar mass and depends on the polarity. So like polar versus non-polar. So if it's polar, then it really depends on the solvent. If the solvent is polar, then it's gonna then this like polar liquid, the polar substance will drive fast. It goes fast like along the paper, and then if it has different polarity, then it drives slow. When we have H2O. Okay, so evaporation is when you separate a solid and liquid. When you're separating a solid that's like soluble in the liquid and the liquid. So if it's insoluble solid, such as like rocks and water, you do the filtration. If it's soluble, such as like sugar and water or like salt and water, then you do the filtration. If it's two liquids with different boiling points, you use a distillation. And then so distillation is for homogeneous, and then filtration is for heterogeneous. Yes. Okay, so for question number D, you guys chose D. Okay. So do more polar substance. So for the chromatography paper, it depends on what the solvent is. And okay, so A is filtration, of course, not filtration, like both are liquids. B is paper chromatography because the liquids will move along this. Okay, so for paper chromatography, as I said, one substance has to be polar, while the other was non-polar. That's when you see the difference in the speed. So for the paper chromatography, how you do it is you have this like paper, and then you're gonna put it in this beaker, and then with a little bit of solvent at the bottom. Right? Okay, and then you are gonna put a dot of the mixture right here, right above the solvent level. And then the solvent will just go up along the paper, and then the solvent will drive the liquid to go upward, but they have different speed, and it depends on polarity. If one of the substance A has the same polarity as solvent, then it's gonna go faster. Let's say B has different polarity from the solvent, then it's gonna go slower. So that's when it gets separated. But for these two, hexane and octane, both are long hydrocarbon chain. Both are long hydrocarbon chain, and both of them are nonpolar. So by using paper chromatography, you will barely see any of the separation. Probably you will see the separation like these, like very little difference, because they have very similar polarity. Both are very, very nonpolar. So it's not going to be paper chromatography, and column chromatography, that's very similar. So stationary phase and then the mobile phase, the mobile phase, and then it also depends on the polarity. And then now polarity is the same. They are both nonpolar. So we can only take advantage of the fact that they have different boiling points. So okay, homogeneous means two substances, they mix thoroughly. They can be mixed very well, such as like sugar dissolved in water, like salt dissolved in water. So heterogeneous is like they cannot be mixed very well, such as when you're oil and water. Oil and water, if you're trying to mix them together, you can still see that like oil layer and then water layer, they're separate from each other. So let's say you have something insoluble in water, such as like sand in water. How do you separate sand from water? So you're going to use the funnel and then the filter paper. So that's what we call by the filtration. And then next, it's the gallium and gas reacts with two of the chlorine gas, and then it forms the gallium tetrachloride. The value of the equilibrium constant for the reaction represented above is 1 × 10 to the power of 10. What is the value of the equilibrium constant for the following reaction? Okay, so you are actually reversing it, and when you reverse it, the products and reactants, they're also reversed. So K, the equilibrium constant, is equal to concentration of the products divided by concentration of the reactants. So that's concentration of the gallium tetrachloride divided by concentration of the gallium divided by concentration of the chlorine gas squared. Okay, and then that's equal to 10 to the 10. For the second reaction, that's going to be concentration of the gallium squared multiplied by concentration of the chloride gas to the power of 4 divided by concentration of the gallium tetrachloride squared. So so denominator and numerator, they are switched. So it's going to be reciprocal of 10 to the power of 10. Okay, and then everything is squared because the coefficients got like 2 times bigger. So you are going to square it. So now that's going to be 10 to the power of negative 20. The answer is A. Okay, so any question regarding this? Any question regarding question number 7, the equilibrium constant? Explain 7 again. Okay, so for 7, so first off, the equilibrium constant is equal to concentration of the product divided by concentration of the reactant. And then you raise the concentration to the power of the coefficient of the species. So that's gallium trichloride. Gallium, wait, not tri. It's tetrachloride divided by gallium and then divided by the chlorine gas squared. And that's 10 to the power of 10. Okay, and then let's say first up, you are going to multiply each side by 2. So 2 gallium, 4 chlorine, and then 2 gallium chloride. Then now you're actually raising all of the concentration by 2. So now it becomes 10 to the power of 10 squared, which is 10 to the power of 20. And then now you're reversing the reaction. When you're reversing the reaction, the reactant becomes the product becomes the reactants. So from here to here, you're actually flipping this fraction. So now denominator and numerator, they are switched. So you're taking reciprocal of 10 to the power of 20, which is 10 to the power of negative 20. Yes, and then question number 8. To catalyze a biochemical reaction, an enzyme typically, Okay, so an enzyme is just like the catalyst, but it is a terminology that you use in bio. It drives the reaction to completion by consuming the byproducts of the reaction. So catalyst does not consume anything. So catalyst is consumed and then it's reformed later in the reaction. So eventually it's not consumed. So A drives the reaction to completion. That's not right. And B binds temporarily to reactant molecules to lower the activation energy. Yes. So it binds to the reactants. So it brings the multiple reactants together to one site so they can react. They can go through the reaction more easily. And then after the reaction is done, it gets detached from the reactants. And C dissociates into additional reactants. No. So catalyst does not dissociate. D decompose and release energy. It does not release energy or absorb energy. Yes. So all of you got B. Great. Okay. And then the next one is question number 9. Of the following diagrams, which best represents the structure of solid potassium fluoride? So potassium fluoride is a ionic compound. So for the solid, for a ionic solid compound, they have cation, anion, cation, anion. They have this like highly ordered structure. So of course that's going to be B. Okay, what's wrong about A? You have a chunk of anions. You have a chunk of anions. No, it's not right. So unlike charges attract, like charges repel. So negative charge and negative charge, they repel each other. They cannot stay together. So that's the same for C. Like unlike like charges, they cannot be arranged in one single row. They're gonna repel each other. And D, okay, so what about D? So D is more of the gaseous state of the potassium fluoride. Yes, we don't need to know what enzyme it is. We just need to know that that is the catalyst. That's another name for the catalyst in biology. Okay, and then the next, okay, obviously the galvanic cell. And then the voltmeter is used to measure the voltage difference. And then zinc and silver. Okay, so now you are given the half reaction for zinc and silver, and you are given this, the reduction potential for each of the metal. The standard reduction potential for the half reaction is shown above, blah, 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 and then the reduction potential is given. Which of the following is a net ionic equation for the overall reaction that occurs as the cell operates? Okay, so if I want the cell to operate, because this is a galvanic cell, which means it's spontaneous. So delta G is less than 0, and then the cell potential has to be greater than 0. Okay, so because both of them are half reaction, I will have to flip one of the cell potential. So either it's going to be positive 0.8 plus positive 0.76, or that's going to be negative 0.8 plus negative 0.76. And to get a positive cell potential, obviously it's the first one, not the second one. Okay, so for the first one, which one do you have to flip? You will have to flip the second one. So the second reaction, the second half reaction becomes zinc release 2 of the electrons and become zinc cation. Okay, and now you're going to combine these two half reactions. Remember, when you combine the half reaction together to write the overall reaction, you have to consider the stoichiometry. So it is 2 times the silver cation and then 2 electrons to get 2 silver. So the electrons get canceled out. So eventually that's 2 silver cation react with 1 zinc. So to produce 2 silver atom and then zinc cation. So the answer is D. Oh, you got C? Wait, 11C? Oh, you're calculating should be 1 with 2 silver. Yes. Silver and zinc, the mole ratio should be 2 to 1, because for the silver, you get only 1 electron transfer. For zinc, you get 2 electron transfer. We need to match the number of the electrons. Yes, when there is a salt breach, and then you assume that this is a galvanic cell. And also you can see if it has the power or not. If it has a power, then it is an electrolytic cell. For this one, you only have voltmeter. It's used to measure the voltage difference, but it does not provide any of the power. So this is this should be the galvanic cell, in which the redox reaction occurs naturally. And then for 11, what is the value E for the cell? Okay, so we're just going to add up these two values, and then that will be 1.56. Again, you are not multiplying this by 2. So even though when you're writing the overall reaction, you have to match the number of the electrons and multiply each of the species by 2, you are not multiplying the cell potential by 2. You didn't get question number 10. Okay. I will go over the question number 10 one more time. Okay, so this, there are two separate containers, and then we have a salt bridge. And then we have the voltmeter, which measures the potential difference, but we don't have external source of the energy, which means it does not provide external energy. So this is a galvanic cell in which the redox reaction occurs naturally or like spontaneously. And for galvanic cell, the cell potential has to be greater than 0. So I need to figure out that which one is the reduction and which one is the oxidation, because only the reduction is given in the table. And how I determine it is by calculating the cell potential for each scenario. Scenario 1, I am flipping the second reaction, okay? Then the cell potential will be 0.8 plus 0.76, which is positive. Scenario number 2, if we're flipping the first one, then it's negative 0.8 plus negative 0.76, which gives me a negative value, negative cell potential. So negative cell potential means it does not occur spontaneously, so it cannot occur in this galvanic cell. So the answer should be the first one, which means I am flipping the second one, the second half reaction. When you flip the second half reaction, it's zinc releasing 2 electrons, and then it forms the zinc cation. And now you will have to combine 2 of the half reactions to write the full or the overall reaction, the overall chemical equation. Okay, but when you're combining them, you will have to consider the number of the electrons. The number of the electrons on the reactant side and product side need to match. So for this half reaction, now I have only 1 electron on the reactant side, and then 2 electrons on the product side. So you will have to multiply this by 2. So now I have 2 silver cation and then 2 electrons and then 2 silver atom as the product. Now the number of the electrons match on the reactant side and product side, so I just add them up. So eventually it's 2 silver cation combines with zinc atom to form 2 silver atom and then zinc cation. So if both of the half reaction have a positive cell potential, do you flip the reaction with a smaller? Yes, exactly. What about for electrolytic cell? If it's electrolytic cell, then you're going to pick this one, which gives me a negative cell potential. Because for the electrolytic cell, they are in the cathode and anodes, they're immersed in this one single container. Yes, the cell potential doesn't change when you're doing the balancing and multiplying it by 2 or 3 or 4 or 5. The cell potential is always the same. So how I explain it is, so this is actually relevant to physics. So this is like the cell potential. So cell potential is like the height difference. Okay, so let's say for cell potential, it actually means the electrons are dropping from a higher energy level to a lower energy level. So the electron flow calls the electricity. So electron flow. So think of it as the water flow. And then when you have, you need to have this like height difference to make sure that water flows from one place to another place. If it's on the level, on the horizontal plane, the water doesn't move. It's just like water just stays there. And then when you have a lot of water or very little of water, it doesn't really make the difference in the direction of the water flow. So a lot of water flow just means that there are way more water like that flows within a unit period of time. But it does not change the fact that water always moves from the high level to a lower level. So that's the same when it comes to cell potential. So when you're multiplying by 2, it just means there are more electrons moving, but the difference, the height difference is still the same. The cell potential doesn't change. Okay, so the next question number 12. carbon dioxide reacts with 2 moles of the lithium hydroxide in solid to become lithium carbonate in aqueous and water. In a one-person spacecraft, an astronaut exhales 880 grams of the carbon dioxide per day. To prevent the buildup, a device containing lithium hydroxide in solid is used to remove that. Okay. So this is a typical stoichiometry question. So what you're given is the mass of the reactants, and now you're asked to find the mass of the of another reactant. Okay, so you're doing a conversion between mass. And then when you are given the balanced chemical equation, there you can't do direct conversion between mass and mass. You can only do direct conversion between mole and mole. So going from carbon dioxide to the lithium hydroxide, you can do a mole conversion. Like 1 mole of carbon dioxide corresponds to 2 mole of the lithium hydroxide. So first off, I will have to convert the mass of the carbon dioxide into its mole. And then I'm going to do the mole conversion, convert it to mole of the lithium hydroxide. And then I convert it back to the mass of the lithium hydroxide. So mass of the carbon dioxide is 880 grams per mole. And then you are going to divide it by number of molar mass of the carbon dioxide, which is 44 grams per mole. And then it's the mole conversion between carbon dioxide and the lithium hydroxide. So for every 1 mole of the carbon dioxide, 2 moles of the lithium hydroxide is consumed. So this is the mole conversion. Now I got the number of moles of the lithium hydroxide. And then I'm converting it back to the mass by multiplying it by the molar mass of lithium hydroxide, 24 grams per mole of the lithium hydroxide. So the answer is 880 minus divided by 44 times 2 times 24, 960. You keep getting C. Probably you didn't multiply by 2. So the mole ratio between mole conversion between carbon dioxide and lithium hydroxide. For every 1 mole of the carbon dioxide consumed, 2 mole of the lithium hydroxide is consumed. So you have to multiply by 2/1 mole ratio. While you self-study Unit 9? So this is, I don't think the practice test, I think it will be about the same or probably a little bit more difficult. Okay, so I can't really tell about like how difficult it is. As I said the last time, like when I took the AP Chemistry, that was 10 years ago. It's like far like yeah. Okay, any other question regarding this, regarding the stoichiometry? Okay, so it seems like there is no question for question number 12. Okay, and then question number 13. So, okay, time, you are given the time, and then you are given the concentration of the nitrogen dioxide. You are given the ln of the concentration. You are given the reciprocal of the concentration. Well, so once I read this table, I know immediately this is the rate. This is kinetics. This is about the rate law. The data from a study of the decomposition of nitrogen dioxide to form nitrogen monoxide and oxygen are given in the table above. Which of the following rate law is consistent with the data? Okay, so again, so remember that for the rate law, we only study the zeros order, the first order, and then the second order. And then each of them will give you a linear graph. But for different y value. Okay, so for the zeros order, it gives me a linear graph when it is the concentration of the reactant over time. And then for the first order, it gives us a linear graph when it's ln, concentration over time. And then for the second order, it gives us a linear relationship between the reciprocal of the concentration and time. So now, taking a look at the table, the increment between each of the time data is 100. It's always the same. So I just need to find another group of data which has the same increment between consecutive data. Okay, for nitrogen dioxide, it decreased by negative like 0.14, and then it decreased by negative 0.08, decreased by negative 0.05. So obviously the increment is not constant. So it's not NO2. And then for ln NO2, the increment is negative 0. Like approximately negative 0.3, negative 0.25. Again, the increment is not constant, so it's not that one. The next, it's positive 0.75, positive 0.75, positive 0.75. Okay, so the increment is constant when I'm comparing the time and then the reciprocal of the concentration. So it must be the second order. So it's rate times K times the concentration raised to the power of 2. So the answer is B. Yeah, like this year you have 60 MCQ questions rather than 50, so I feel like it will be more difficult. Wait, can anyone see my screen? I feel like it's getting blurry for some reason. If the rate order is equal to 0, then rate law is just rate is equal to K. Yes, perfect. Oh, okay. Probably I'm experiencing some Wi-Fi issue, but yeah, let me know if you can see it. How is it B and not C? Okay, so when you have a linear relationship between the time, okay, again, this graph is a linear relationship between the concentration, reciprocal of the concentration and time. And this is rate versus the concentration. It's like two different graphs. This is rate versus the concentration of the reactant. And when I say rate law, okay, so according to the rate law states that rate is equal to the reaction rate constant K multiplied by the concentration to the power of X. So X represents some positive integer. Well, it might be 0. So let's say it's a whole number. It can be 0, 1, 2, 3, 5. And then based on this graph, when you're comparing the concentration versus time, if you get the linear relationship between the reciprocal and the time, then this is a second order, which means X is equal to 2. Well, this is actually... so in AP Chemistry, you are not required to do the calculus part, but you can actually use the integral. If you ever learn the calculus, you can do the integral. You can try it by yourself. And then if you go backward from here to here, then you will get you will get that it's K times the concentration to the power of 2. Is A of first order? Yes, A is first order, B is second order, and C and D just doesn't make sense. Because for the rate law, we always specify that X has to be a whole number that's greater than or equal to 0. So we don't see something like negative 1 order or negative 2 order. Okay, next. Okay, so binding energy again. So it must be about the electron configuration or atomic structure. Question number 14, the photoelectron spectra for hydrogen and helium. Okay, so what is photoelectron spectra? So for an atom, so it consists of the nucleus, which has the proton and neutron, and then surrounded by electrons. Okay, so let's say this is the first shell, you have 2 electrons. On the second shell, let's say you have 1 electron. So for example, this is, let's say this is like lithium. So photoelectron spectra shows the amount of energy needed to remove each of the electron from the outermost shell. So from the outermost shell, when you remove this electron, then it requires like a little bit of energy. But when you're trying to remove these 2 electrons, which is the core electrons, then it requires more energy. So you will see a peak more towards the left. So remember for these like binding energy graph, when you're going to the right, it's always small energy. When you go to the left, it's always the greater energy. So for this one, the photoelectron spectra for the hydrogen and helium. Okay, so hydrogen has a lower peak, helium has a greater peak. So the height of the peak represents the number of the electrons. So helium has twice as high peak as hydrogen. That's of course because helium has 2 valence electrons while hydrogen has only 1 valence electron. So which one best accounts for the fact that peak of the helium is farther to the left? Oh, and higher. Okay, so for the higher, it means it's 2 valence electrons, while it's only 1 valence electrons for hydrogen. And then when it's farther to the left, it means, okay, the greater energy. So which means the binding energy is bigger, or ionization energy is bigger. And this is because helium has twice as much effective nuclear charge. It has 2 protons. So the electrons experience a greater attraction force toward the nucleus. So they're bonded stronger toward the nucleus. So it's like harder to remove them. So helium has an additional valence electron in a higher energy level. Okay, so this part is not right. So helium and hydrogen, both of them are on the first energy level. They're on n equals 1. So higher energy level is not right. A is not right. B, helium has a greater nuclear charge than hydrogen and an additional electron in the same energy level. So B, that is the right answer. So and C, helium has a completely filled valence shell electron well, which is true, in which the electrons are a greater distance from the nucleus. Okay, so that's not true. So on the periodic trend, according to the periodic trend, when you go from left to the right on the same energy shell, on the same energy level, the atomic size decreases because of the greater number of the protons, because of the increasing effective nuclear charge. So it's getting smaller and smaller and smaller, because of the stronger attraction between the nucleus and the electrons. So stronger attraction means they shrink. So when you go from left to the right, the atomic size is getting smaller, so helium is smaller. D, it takes longer for the electrons. Well, it has nothing to do with time. So time has nothing to do with the binding energy. So B, because it's farther to the left when it has higher energy or higher nuclear charge, and it's higher because it has additional valence electron. Yes, great. So nuclear charge means exactly, okay, literally it means the number of the protons. So hydrogen has 1 proton, and then helium has 2 protons. So helium has a greater nuclear charge than hydrogen. Why is D wrong? Okay, C, helium has completely filled valence shell. So the first part is correct, in which the electrons are a great distance from the nucleus. No. So when electrons are a great distance from nucleus means it has a bigger atomic size. That's not right. When on the periodic table, when you go from left to the right, the atomic size decrease because your nuclear charge is getting bigger because of the increasing number of the protons. So the greater attraction between the protons and the electrons make them shrink a little bit, little by little when you go from left to the right. So the distance between the electrons and nucleus is getting smaller. So it's smaller than hydrogen, not bigger than hydrogen. So if it's added into the level 3D, is that the 4th or 3rd energy level, since it's after 4? That's still 3. What really matters is the number. So 3D is n equals 3. 4s is like n equals 4. So when you say, yes, it's the opposite. So it should be like smaller distance. It should be smaller distance rather than greater distance. Yes, Moktos, thank you for explaining that. And next question. Okay, so we have a bunch of compounds to compare. And we're given their Lewis dot diagram, their structure, and we're given the molar mass. And then this is the combustion reaction, obviously, the enthalpy change of the combustion for each of the compound. 15, which of the following is the molecular formula of the unknown compound? Okay, so you're going to determine it based on this combustion reaction. Because for this combustion reaction, it formed the carbon dioxide and then the hydrogen, the water molecules are formed, which means it consists of carbon, hydrogen, and oxygen. So this is basically just balancing the equation. So on the product side, I have 4 carbon and then 8 hydrogen, and I have 4 times 2 plus 4, which is 12 oxygen. Okay, which means on the left side, I should have exactly the same number of the atoms for each of the species. I already have 10 oxygen for 5 moles of the oxygen gas, which means for this unknown compounds, I should have 4 carbon, 8 hydrogen, and 2 of the oxygen. So these 3 combine together to form C4H8O2, which is C4H8. C4H8, which is D. Yes, so D is the right one. Okay, all of you guys are getting the right answer. Great. Okay, let me try to... I feel like I'm blocking some of the problems. Okay, D, great. And question number 16, which of the following best explains why the combustion reactions represented in the table are exothermic? Okay, for all of this combustion, it's exothermic, which means releasing energy. Remember that all the combustion reactions are exothermic reaction, and then it makes it raises the temperature of the surroundings. It's because, okay, so a number of the bonds in a reactant molecules is greater than the number of the bonds. Okay, so it's not really about the number of the bonds. So how do we calculate the enthalpy change for a reaction? If we ever use the bond enthalpy, because it says energy required to break the bonds. That's the bond enthalpy. Then it's bond enthalpy required for the reactants minus bond enthalpy required for the products, which means okay, and then this is a negative value, which means the bond enthalpy required to break the reactants is actually smaller. And then when the new bonds are formed, it releases a lot of energy. So C, energy required to break the bonds in a reactant is greater. No, if it's greater, then you will get an endothermic reaction. D, the energy required to break the bonds in reactant is less than the energy released in forming the bonds in the products. Yes, so D is the right answer. So if it's like positive, and both are positive values because it's energy required to break the bonds. So it's a small value minus a large value. So eventually you get an exothermic reaction. Is it isomerism in our spec? No, you're not required to memorize like anything about isomerism. Okay, so the answer is D for question number 16. And then next, question number 17. So based on the structural formula, which of the following identifies the compound that is more soluble in water and best helps to explain why? So solubility, it's all about the intermolecular force. So when two substances have similar intermolecular force, then they tend to be soluble with each other. So water molecule, so hydrogen bonding is the primary one that connects the water molecules all together. So it must be something that has the hydrogen bonding or very, very strong like ion dipole force or like dipole-dipole interaction. So when we're comparing ethane and propanol, okay, so this is ethane, this is propanol. So ethane is like perfectly symmetric. Ethane is perfectly symmetric and it's nonpolar, because it's a nonpolar molecule, which means it has the London dispersion force only. And then propanol has like hydrogen covalently bonded to an oxygen, which means it can form a hydrogen bonding. So it has hydrogen bonding, LDF, and then dipole-dipole interaction. So of course, propanol dissolves like better in water. So not A or B. Okay, and let's take a look at the reason. Its molecules have a greater mass. Okay, so it has nothing to do with a molecule, the greater mass. So sometimes it does matter if we're comparing the London dispersion force of two different molecules, then greater mass means more atoms means more electrons. It means higher polarizability. So the greater London dispersion force. But when it comes to hydrogen bonding, it has nothing to do with greater mass. So the answer is D, because it can form hydrogen bonds with the water molecules, but those of the ethane cannot. Do all the OH alcohols end with yes? They all end with OL, like propanol, like ethanol, methanol, yes, like hexanol, heptanol, like decanol, all of them that ends with OL. Left, right, or reactants minus products? Oh, do you mean the bond enthalpy? Yes. So for all the other types of calculation, it's always the final minus the reactant or products minus the reactants. But when it comes to bond enthalpy, you're breaking the bonds in reactants, and then the bonds in the products are formed. So it's the opposite, reactants minus product for the bond enthalpy. Question number 18, in an experiment, so 30 grams of ethane and 30 grams of propanol are placed in a separate reaction vessels, and each compound undergoes a complete combustion with excess oxygen. So excess oxygen means for both of the reaction, the limiting reagent is either the ethane or the propanol, so not the oxygen. Which of the following best compares the quantity of the heat released in each combustion reaction? Okay, so it's 30 grams for each of them. And then for the enthalpy change, it's measured per mole. So what's really matter is not the mass, it's the number of the moles. So for 30 grams of ethane means it's 30 grams divided by 30 grams per mole, or that's 1 mole of the ethane. So 1 mole of ethane multiplied by this value. So the amount of heat released by ethane combustion is 1560 kilojoules. That's Q ethane. Okay, on the other hand, when you have 30 grams of the propanol, you have only 0.5 moles. So when you multiply 0.5 moles with this value, you get approximately 1,000 kilojoules. So the amount of heat released by the propanol is actually less than the amount of heat released by the ethane, just because it's only 1/2 mole. So QE is greater than QP. So ethane combustion of 30 grams of ethane produces more heat. Is there ever a point where molecules with LDF have a stronger intermolecular force than the hydrogen bonds? Yes. Okay, so very simple. Think of like the cooking oil, the oil used every single day at home to do the cooking, like whatever the canola oil, like olive oil, all kinds of oils. So those oils they're actually the fatty acids. So different fatty acids have different structure, and then it's organic chemistry. You don't learn it in AP chemistry, but let me explain it. Then fatty acid means it has a very, very, very long hydrocarbon chain. And then at the end, you might have like a little bit of oxygen, like 1 or 2 oxygen. You might have like one more oxygen here. But anyway, it's a very, very long hydrocarbon chain. So primarily, it's the London dispersion force that's working to make sure that these fatty acids and molecules are stick together. So intermolecular force, the primary intermolecular force in all of these fatty acids are LDF. But when you're comparing the boiling point of water and the boiling point of the, let's say, vegetable oils, of course, the oils have a much higher boiling point. And it's because their hydrocarbon chain is so long, so their London dispersion force is so big. So they tend to have a stronger intermolecular force than water. It also explains why like water is like more viscous or like more sticky compared to water. So viscosity, like the stickiness, also depends on intermolecular force. So like oils have very high very strong intermolecular force, so that's why they're more viscous. Oh, okay. So I will try to explain why the radius of the iron 2 plus is larger than the radius of the iron 3 plus. Okay, so both of them are iron, which means both ions have the same number of the protons, right? Okay, then which one has a fewer number of the electrons? So 3 plus means it has lost 3 electrons. So iron 3 plus has a smaller number of electrons. That's one thing. Okay, the second thing is Fe2 plus. Okay, so for the Fe2 plus, when it has lost 2 of the electrons, then well, actually no. Okay, so Fe3 plus, it has lost 3 electrons, which means fewer number of the electrons. Okay, so there are 2 ways to explain it. One is each of the electron will now experience a greater attraction toward the nucleus. So let's say, for example, 10 electrons versus like 10 protons. Then each of the electron get to have an average of 1 proton, right? But when you have, let's say, 8 electrons versus 10 protons, then in the second scenario, every single electron gets to experience a little bit more or a little bit stronger force compared to this one. Because in 10 electrons, 10 electrons divide that force, and then for 8 electrons, only 8 of them divide the attraction force. And then that's one way to explain it. The other way is the fewer core electrons. So core electrons means electrons inside. So fewer core electron means there are less of the electron shield or less of the electron-electron repulsion. So when you're comparing the atom or the ion, which have the same number of the protons, the fewer electrons always means the greater attraction between the outermost electrons and then the nucleus. So it's going to experience a greater attraction force. So it's going to shrink a little bit more than Fe2+. Would we talk about the Coulomb's law? You can mention Coulomb's law, but you're not required. So even if you don't mention the Coulomb's law, if you can properly explain it, you will still get the points. And next is question number 19. And then can you explain the answer again? Okay, I will try to explain the answer again. So now we have 30 grams of ethane and 30 grams of propanol. So the mass is the same. But what really matters when it comes to the enthalpy change for a reaction is not the mass, it's the number of the moles. Because for enthalpy change of the combustion or formation or the reaction, we always measure it using a unit of kilojoules per mole, not per gram. So I will have to figure out the number of moles of the propanol and ethane. And how I do it is mass is equal to number of moles times molar mass, which means number of moles is equal to mass divided by the molar mass. So 30 grams divided by ethane's molar mass 30, which means you have 1 mole of ethane. So when 1 mole of ethane goes through the combustion, the amount of heat released is 1,560 kilojoules. On the other hand, you have only 0.5 moles of the propanol. And then when that amount of propanol goes through the combustion, only 1,000 kilojoules, 1,010 kilojoules are released. So that's why ethane releases more energy than propane when both 30 grams of the samples are going through the combustion. So that's why the answer is C. Q ethane is greater than Q propanol. And next, question number 19. A sealed 10 liters flask at 400 Kelvin contains equal molar amounts of ethane and propanol in gaseous form. Which of the following statements concerning the average molecular speed of ethane and propanol is true? Okay, so it's about the average molecular speed and then about ethane and propanol. So remember the average kinetic energy. This is super important. So average kinetic energy is only related to the temperature measured in Kelvin. So it's the same as the temperature measured in Kelvin. So if when these two species have exactly the same temperature, they have the same average kinetic energy. But this doesn't mean that they have the same average molecular speed, because kinetic energy is equal to 1/2 times mass times the velocity squared. So even though they have the same kinetic energy, but whichever has a greater mass will have a lower speed. And at ethane and propanol, which one has a greater molar mass? So propanol has a greater molar mass. So propanol with a greater molar mass will have a lower speed. So the average molecular speed of ethane. So again, propane has like bigger mass, so its speed is smaller. So average molecular speed of the ethane is less. No, that's not true. B, average molecular speed of ethane is greater than. Yes. Okay, so for this, remember that when two species or when two gas particles have the same kinetic energy, then their speed V1 over V2 is the square root of M2 over M1. So M1, M2 represent the molar mass. So speed of the ethane to speed of the propanol is equal to the square root of molar mass of the propanol to the molar mass of the ethane. And obviously, propanol has a greater molar mass, so ethane has a greater speed. This formula, I forgot the name. It's called effusion rate. You learn it when you learn the like gas law, the ideal gas law, and then the effusion rate ratio. But I kind of forgot the name of the. I think there's a name, but I forgot the name. I think it's named after some scientist. Okay, any question regarding this? Any question regarding the average speed and then the average kinetic energy of two different gas particles? Remember that it's a reciprocal. Well, to be honest, like it's two hours and like 12 minutes. So probably I will have to stop soon because I have classes later. So does the average molecular speed differ with mass, but average kinetic energy? Exactly. So average kinetic energy only depends on the temperature. Average kinetic energy only depends on the temperature. So for propane, ethane, like propanol, ethanol, for all of them, if they have the same temperature, then all of them have the same average kinetic energy, but they will have different average speed. Oh yeah, it's effusion rate, the Graham's law of diffusion. I'm just really bad at names. I don't really get to memorize the name of all of those scientists. Okay, so question number 20. As a sample of potassium nitrate in solid is stirred into water at 25, the compound dissolves endothermically, which means delta H is positive value. Which of the following best helps to explain why the process is thermodynamically favorable at 25? Okay, so it means delta G is negative value, while delta H is positive. So this is negative, this is positive, okay? Then it must be due to the fact that T times delta X is a greater positive value. So it must be a much bigger positive value. Okay, and it's because delta S is positive value, and that's because when the ionic compounds dissolve in solution, then the ionic bonds are broken, and then the cations and anions are free to move. So the entropy increases. So this is actually a entropy-driven spontaneous reaction. So decrease the enthalpy. Okay, not right. It increased the entropy. Yes. So dissolving the salt increased the entropy, and that's why, as a whole, this is a thermodynamically favorable process. So stirring the solution adds the energy needed to drive an endothermic process. Okay, so stirring doesn't really make it like spontaneous or non-spontaneous. All endothermic processes are thermodynamically favorable. That's also not true. Okay, so next is number 21. A solution is prepared by mixing equal volumes of 0.2 molar of HC2H3O2 and 0.4 molar of sodium C2H3O2. Which of the following correctly describes what occurs if a small amount of hydrochloric acid and sodium chloride or sodium hydroxide is added? Okay, so when you have the equal volumes of these two, and first up, they are acid, weak acid, and its conjugate base. Well, the second one is actually a salt, but when the salt is dissolved in a solution, then it becomes the cation sodium and then the anion. So it's basically the conjugate base. When you have the weak acid and its conjugate base in the same solution, we call it the buffer solution. And buffer solution is really good at resisting the pH change when strong acid or strong base is added. So when hydrochloric acid is added, pH will increase. Well, of course not. Hydrochloric acid, that's an acid, so the pH will decrease, but only by very little amount. And if hydrochloric acid is added, the pH will decrease only slightly because the proton ions are consumed by the conjugate base. Perfect. So conjugate base reacts with the protons and it becomes the weak acid. So the protons are consumed, so it does not affect the concentration of protons as much. So B is the right answer. C, when sodium hydroxide is added, pH will increase slightly, which is true, but hydroxide ions will react with the conjugate base? Of course not. So hydroxide, which is a strong base, reacts with the acid. And D, pH will decrease. Of course, this is not right. Can you explain Oh, the pH curve of the titration. So I already I went over the acid base on yesterday's live session. Not yesterday, probably on Friday's live session. So you can check out the video. The boiling point of the CS2 is higher than that of the CO2, even though CO2 has both London dispersion force and dipole. Wait. CS2. Do you mean the CO2 or carbon dioxide or COS? Okay, so carbon dioxide, and then carbon, oxygen, and carbon, sulfur. So on the periodic table, sulfur is below the oxygen, which means sulfur has more electrons. And then more electrons always mean that it's larger or greater polarizability. So polarizability means the tendency of a molecule to form dipole, to form the temporary dipole. It means how much the electrons can be dispersed within the molecule and not just concentrate, like bonded to one atom. And more electrons means they are more free to move around within the molecule, so greater polarizability, and this means a larger London dispersion force. Conjugate base has the higher molarity, therefore there's still more left and reactive. Okay, mocktail. Wait. We have more conjugate base, yes, because it's equal volumes, but the concentration of the conjugate base is higher. So a greater conjugate base, more of the conjugate base means it's better at resisting the pH change when the strong acid is added. So it can resist a change when either strong acid or strong base is added, but it's slightly better at resisting a change when strong acid is added because it has more of the conjugate base. So it can actually remove more of the protons than removing more of the hydroxide. Yes. So I literally just explained the carbon dioxide versus the CO. Does the polarizability affect the no. Polarizability does not affect solubility. No, polarizability does not affect it. So solubility is affected by only the intermolecular force. So when two species have the same type of intermolecular force, they dissolve pretty well. So that's why if you want to mix different types of the vegetable oils, they blend in very well with each other because within each of the oils, each type of oils, the primary one is London dispersion force. Will I do the FRQ? I don't think I will have time to do the FRQ, to be honest. Okay, the next is question number 22. A mixture of hydrogen gas and oxygen gas is placed in a containers as represented above. The hydrogen gas and oxygen react to form the water H2O, and which of the following best represent the container after the reaction has gone to completion? So for now, we have 4 moles of the hydrogen, and then also 4 moles of the oxygen. So at most, they can form 4 moles of the H2O, and then you will have 2 of the oxygen left over. Not reacted. Okay, so it will be 4 water molecules. I'm looking for the 4 water molecules and 2 moles of the oxygen, which is B. Okay, and next one is question number 23. So after a certain pesticide compound is applied to the crops, the decomposition is the first order reaction with a half-life of 56 days. So first order reaction is the only one that has a constant half-life. And what is the rate constant? Okay, so you can find this formula on the formula sheet. So on the formula sheet, okay, the right here, kinetics. So this one, okay, it's the half-life of the first order reaction. It's ln2 divided by the reaction rate constant K, and the ln2 is approximately 0.693. So you just plug in a number. So half-life is equal to 0.693 divided by reaction rate constant K. So K is equal to 0.693 divided by half-life, which is the half-life is 56 days. And then remember that you always need to include the units. So that's going to be 0.693 0.012 per day. The answer is 23. The answer is A. Okay, and then for question number 24. Which of the following can be inferred from the diagram above that shows the dependence of the potential energy on the y-axis on the internuclear distance between two atoms? So this is a graph that shows how to find the distance between two atoms when two atoms covalently bond with each other to form a molecule. So you are going to find this most stable point. This point with the lowest potential energy means it's the most stable. Why is it not A? No, the answer is A. 23 is A. Do for bio? No, I don't. Okay, so I didn't do bio when I was in high school, and then I'm not very good at bio, but I'm gonna do AP Physics 1. So I'm gonna post more videos on AP Physics 1. If I have time, then I might post videos regarding calculus, but I'm not quite sure because it takes a lot of time to film the videos, so I would prioritize physics. Okay, so which of the following can be inferred, blah, blah. So A, the atom forms a bond with a bond length of 25 pm. Okay, so picometer. So how I find the bond length is spot this point, and then the corresponding internuclear distance is literally just the internuclear distance. So it's in between 50 and 100, so it should be about 75. So either B or D, and then the net force between the atom is attractive. No, so it's going to be B. So this point literally just means that at this point it has the lowest potential energy, or it is the most stable one. It's the most stable state. So high potential energy always means unstable. Low potential energy always means that's stable. Me? I took AP Chemistry exam like 10 years ago. What did I get? I got 5. I took AP Chem, AP Physics B. So back then it's called AP Physics B. It's like a combination of Physics 1 and 2. I took Physics C, Mechanics, and Physics C, Electricity Mechanism. I took Physics Calculus BC. I took, what else? Macro, and then Micro, and AP Chinese. I think that's all I took, and then I got all 5. Why is it B and not D? Okay, so D states in the net force between the atom is attractive at no. Okay, so actually at this point, this is a point that the attractive force and then the repulsive force form some kind of balance. So okay, when atoms are too close to each other, their nucleus are super close to each other. When nucleus are super close to each other, they have a big repulsive force. Okay, but what if two atoms are like super far from each other, like they're like very, very, very far? Then they do not interact with each other. They do not attract, they do not repel, just nothing. They do not interact at all. And when atoms get slightly closer to each other, okay, then they have the attractive force between the nucleus of left atom and the electrons of the right atom. So the attractive force is more predominant. Okay, and when they get too close, it's a repulsive force. So at this point, they find a perfect balance between the attractive force and then the repulsive force. So the net force is not attractive. So the net force, because it's stable, the net force is just 0. That's why they stay together at that distance. So that's why D is not the right answer. Okay, and then 25, a mixture of two gases, 0.01 moles of C4H10, so that should be butane, and 0.065 moles of the oxygen gas is pumped into a cylinder with a movable piston. The mixture originally at 200 Celsius degree and 1.0 atm is spark, and the reaction represented below occurs. Okay, which of the following is true after the product gases return to the original temperature and pressure, and why will the change occur? Assume that all gases behave ideally. Oh, wait, let me reread the question. wait, 0.01 moles and 0.06. Okay. And then after the product gets returned to the original temperature. Oh, okay. So they react. They react at a ratio of 2 to the 13. So after these amounts of the reactants react together, it's gonna produce 0.08 moles of the carbon dioxide and 0.1 moles of the water vapor. Return to the original gas. What will the change occur? Okay, so before the reaction, we have in total 0.075 moles of the gas before the reaction. And after the reaction, we have a total of 0.18 mole of the gas. Wait, is that right? Did I do the calculation right? It's 15 moles and then 18 moles of the gas. Wait, sorry, I think I did a calculation wrong. Oh, never mind. Sorry, it should be 0.04 moles of the carbon dioxide after the reaction and 0.05 moles of the water vapor after the reaction. So it's 0.09 moles of the gas after the reaction. Okay, so the temperature, return to the original temperature and pressure. So, okay, so PV is equal to N times R times T. So the temperature and pressure, temperature has not changed. So pressure has not changed. Okay, and then the number of the number of the gases, the number of moles of the gases has increased from 0.075 moles to 0.09 moles, which means the volume should also increase by that much. Okay, so the piston will be higher than its original position. Yes, so it should be, the piston is higher, so not B. And unchanged, of course, not lower, not. So the answer is A. So for the ideal gas flow, the volume of the gas sample totally depends on the number of the moles. They are proportional to each other, given that temperature and pressure are held, they're constant. Okay, the number of mole of the products. Okay, so to be honest, you don't have to do the calculation. Let's make it super easy. So for this reaction, before the reaction, we have 15 moles of the gas in total. It doesn't matter which one is which reactant is it. After the reaction, 15 moles of gas is converted to 18 moles of the gas. So number of moles of the gas has increased a little bit. Okay, and then now it says the temperature and pressure is not changing. So according to this ideal gas flow, okay, so PV is equal to nRT. So pressure is not changing, temperature is not changing, R, that's the gas constant. So what really matters is number of the moles of the gas and then the volume. So if this increased, then volume also increase. If number of moles of the gas decrease, volume also decrease. So number of mole of the gases has increased from 15 to 18. It has increased, which means the volume should also increase as well. So that's why the piston will go a little bit higher. So the gas can occupy more volume. So it will be A. Okay, so guys, it's 1:30. I'm so sorry. I really want to go over everything, but I have class at 1:30, so I need to leave. So I'm going to stop the live stream session here. And then I will really appreciate it if you can leave some comments on my Google, what is it called? Google business profile. Wait, how do I find my Google business profile? If you type just Academic-Coach-Youhyun, I think it will just show up. So I would really appreciate it if you can leave some reviews there. Yeah, this is our last video. Yeah, I have to leave because I have class at 1:30 p.m. and it's already 1:30. You can just Google okay, or I can just send you the links. Yes, so if you click on the link, I think it will direct you guys to the Google Map page. And then I would really appreciate it if you can leave some comments, the reviews. Okay, so I really gotta leave. Okay, Thank you guys for joining, and then good luck on tomorrow's exam. And then I will post more videos on AP Physics 1 for sure. So if any of you guys are taking it or any of your friends are taking it, you can just let them subscribe to my channel, and then I will do more live session for physics as well. Bye guys. Good luck on your AP Chemistry exam tomorrow. Good luck and have a good sleep. Don't try to study overnight.